Our speaker today is Dr. Sabrina Stierwalt. She is an extragalactic astrophysicist. She uses nearby intergalactic galaxies to understand how stars and galaxies form throughout the universe's history. She uses data from space-based telescopes like Hubble, Spitzer, and XMM Newton, along with data from ground-based telescopes like ALMA and VLA and Magellan. Most recently, she was awarded a multi-year grant from the National Science Foundation to conduct the first systemic study of gas dynamics and star formation in the interacting dwarf galaxies, which are smaller galaxies, which are building blocks of more massive ones like our Milky Way. She also works to make science and the stars more accessible. She does this with her weekly science podcast, Everyday Einstein, through a program, and I can highly recommend the podcast. They're short podcasts, and she demystified blood last week. Very good, thank you, doctor. And building blocks of more massive ones like our, I'm sorry, and I am going to just turn it over to Dr. Stierwalt right now. Thank you, Dr. Stierwalt.
Thank you for having me. I have an assistant with me as well. This is Ivy.
Hi.
All right. All right, can everyone see that? Yes, okay. So I'm Dr. Sabrina Stierwalt. Thank you for having me. And this is my assistant, Ivy. And hi. And we are, look up here. We are going to talk to you today about black holes. So the news is a little tough out there right now. And so I hope that you will come with us on a journey into one of the most mysterious objects that the universe has to offer, and that's a black hole. All right, so a black hole is a region of space where things get so compressed, so squashed down that, thank you, that not even, the gravitational pull is so strong that not even light can escape. So that means technically anything can become a black hole. So you can become a black hole, your couch, I assume you're sitting at home on your couch, your apartment. If we squeeze these things down small enough, then they will become a black hole, where the gravitational pull is so strong that when light tries to leave, it gets bent back inward. So our Earth, which is about 8,000 miles across, would become a black hole if we compressed it down, so it would become dense enough to be a black hole, where even the fastest traveling thing we know, light, can't escape. If we compressed it down to the size of a
Penny.
A penny, that's right. So we'd have to get it down to the size of a penny in order to be able to see it. Sorry, I see someone, I see Laura typing, that's not, is it for me? No, yes, no, okay. Compress it down to the size of a penny. So back in the 1700s, this gentleman named John Michell, who's described as a philosopher and a clergyman, predicted that we might have these things called dark stars that were so, their gravitational pull was so strong that not even light could escape. Now, he had no business predicting this. He had no scientific backing to think that this might be the case. So I imagine he was just sitting around with his friends one night thinking, hey man, what if there were stars that were dark or something like that? I don't know where he got this idea. But he's described by the American Physics Society as being, quote, so far ahead of his scientific contemporaries that his ideas languished in obscurity until they were reinvented more than a century later. So haven't we all felt like that? Nobody gets me. It must be because I'm just ahead of my time. So John Michell predicted that there could be these things called dark stars. And now we actually know a physical mechanism that can compress something so far down, so small and so compact that the gravitational pull is so strong that not even light can make its way out. Now, we talked about you'd have to take the Earth and make it to a size of a penny. You'd have to take a mountain and compress it down to the size of, say, an atomic nucleus. Even something like the sun, you'd have to take the sun, which is much, much larger than our Earth, and compress it down to about 3 kilometers in size. But we don't really know any physical mechanisms that can take such small objects and compress them down so small. But we do know that if you start with a much larger object, like a larger star, so our sun, sorry to say, very special to us, but very average according to the rest of the universe. So if you take a star that's larger than our sun, and at the end of its life, so for most of a star's life, it burns through the hydrogen fusion in its core. It makes energy that radiates outward and makes it shine, great for us. And then, so this also, the pressure from all these photons, all this light making its way out of the star, counteracts the gravitational pull that wants the star to collapse in on itself. So there's this great balance between these two things, the star making energy through fusion in its core and gravity trying to push back down, that we call this hydrostatic equilibrium that helps a star live in somewhat harmony for a lot of its life. But then eventually it runs out of that fuel. And what we have is a disastrous event where eventually, with nothing pushing back, gravity takes over and gravity wins. And so that incredible crush of gravity on this star that started out larger than our sun, eventually those outer layers come crashing down. They bounce off the core that's left there, and you get this huge explosion called a supernova. And then once that material fades away out into space, you're left with the core of that very dense object, which is a black hole. So you've taken a large amount of mass and you've compressed it down into what we call zero volume. So you've made a black hole. So now we know there's a physical mechanism for making black holes. Now, something so dense with such a strong gravitational pull that not even light can escape. I keep saying that, but what does that actually mean? Well, Einstein's theory of general relativity tells us that a massive object will curve the space-time around it. So this is sort of a little depiction of how you can think about that. So a light ray traveling by this massive object will think it's traveling on a straight path, but if it's traveling along one of these pink lines here, it actually is traveling on a bent path because the space around this object is getting bent. The more massive the object, the bigger that curve or the bigger that bend in the space-time around it. So all massive objects curve space-time. You curve space-time, but to such an imperceptible level because we're not very massive. And so we've actually tested the sun curves the space-time around it, and we tested this using the Viking lander. So this was a really great test of Einstein's theory of general relativity, which seems kind of out there. Okay, you're bending space and time, but you can actually physically test it. And the way we did this was with the Viking lander, when it was on the opposite side of the sun from us, sorry, my computer's acting up. I hope that doesn't mess up the sound. The Viking lander, we measured signals coming from the Viking lander to Earth. And we thought that it should take a certain amount of time, but it actually took longer. There was a time delay, and that was because those signals weren't traveling a straight line. They were actually traveling this much longer curved path because they were going into this curve in space-time created by the sun. Now, I keep saying space-time, so not only is space curved around a massive object, but also time. So time moves more slowly when you're in the presence of a strong gravitational field. Now that means that here on Earth, on the surface of the Earth, the gravitational pull of the Earth is just a little bit stronger than it is, say, for satellites up in space. And so that actually is something we can measure when it comes to, say, GPS satellites. So since we feel a little bit more gravity here on Earth than the satellites do, time passes a little bit more slowly for us. And that means that if we didn't correct for this time difference, our GPS satellites would get off by 45 microseconds every day. That doesn't sound like very much, but it means you could be off in your destination by as much as 7 miles. I don't know about you, but I'd be pretty ticked if I wound up 7 miles away from where I was trying to get with my GPS. So gravitational pull of a massive object curves space and it curves time. So since time passes more slowly in the presence of a massive object, let's say, for example, you wanted to escape this current timeline. I don't know why you would want to do that. Return in 2021. You could go hang out in the presence of a massive black hole for a couple of days and come back. And more time would have passed here on Earth than it would have for you because you were hanging out in the presence of a strong gravitational field. Unfortunately, when there are other adverse effects to hanging out around a massive black hole. So for example, gravity is really strong. So we talked about how the gravity here on Earth is a little bit stronger than what GPS, the gravitational pull that our satellites feel out in space, because they're a little bit farther away. I'm sorry, my assistant is yawning. So the same is true for our feet versus our head. So the gravitational pull that we feel on our feet is a little bit stronger than the gravitational pull that we feel on our head because your 5 to 6 feet difference between these two spots on your body. That since the Earth isn't very massive, astronomically speaking, that difference in gravitational pull doesn't really affect us, obviously. But in the presence of a massive black hole, there is a big difference because the gravitational field is so strong. And so your feet feel a lot stronger gravitational pull than your head. And so that ends up stretching you out in a process that is officially called spaghettification. So you might escape the pandemic timeline here, but you'd be turned into noodles. All right. So how do we detect these things if they're dark and light can't escape? They don't emit any light. Well, here is an image, an astronomical image of the region of space where the first black hole in our galaxy was detected, called Cygnus X1. And so you can see it's mostly dark around this black hole when we look in optical light. So we're not seeing that normal light like we would from a bright star. And it was actually detected with the Uhuru satellite in the 1970s. And so the reason we can detect these black holes is that here is an artist's depiction of, so this is an illustration, not an actual astronomical image, but it gives you a really good idea of how we can detect these black holes. So they're not shining out light like a star does, like a normal star. But when matter gets close, any sort of material gets close to the black hole, it doesn't suck it in immediately. It's not some sort of cosmic vacuum cleaner. Instead, it hits a disk, it swirls in a disk of material that can eventually swirl into the black hole. So we call these accretion disks because the black hole slowly accretes material. And so one way it can do this, if it has a massive companion star, so that's this big blue thing here, this star is burping out a lot of material. This happens when a star gets to the end of its life. It's starting to run out of fuel. It does a lot of sputtering and burps out a lot of gas. And so some of that gas will get closer to the black hole. And as it comes in and it hits this disk of swirling material, that causes a lot of friction as it hits. And so if you rub your hands together, assistant, rub your hands together, what happens? They get hot, right? So that's from the friction. And so when this material comes in, hits the disk, you get all this friction and it heats up. And so it emits a lot of, thank you, that's perfect. It emits a lot of energy, hot radiation that we can then detect. So we're not actually seeing the black hole itself, but we're seeing the effects on its surroundings through this hot gas that it's emitting. So this is one of the main ways we can detect black holes and see that they're there. So far we've been talking about stellar mass black holes. These are black holes that we can find in our own galaxy that happen when a large star hits the end of its life. But we also have supermassive black holes. So stellar mass black holes are something like 10 to 100 times the mass of our sun. But there are also things called supermassive black holes. Supermassive, official term, which are something like billions of times the mass of our sun. And these exist, we find these in the centers of other galaxies. So these stellar mass black holes, we mostly find them in our own galaxy because they're smaller, so they have to be close by. But these supermassive ones are so big that we can see them much farther away. They're so bright with these accretion disks that we can see them in other galaxies. And they also emit, here's a nice astronomical image of one of these with jets. They're so strong that they often have jets coming out. And so one of the leading researchers in these jets, these powerful jets that are emitted by these supermassive black holes as they gobble up surrounding material, is Dr. Jajida Ishler. And she's done a lot of great talks, TED Talks, National Geographic talks. So I highly recommend checking out her work if you want to hear more about this stuff. So, all right. So here is, let's see if my movie will play. So here's a simulation of that accretion disk, which I just think is really neat. I could watch it for a long time. And so what you're seeing here is that disk of swirling material, and we're gonna look at it from different angles. But you also see emission on the top and on the bottom. And that's because you're gonna have some light that gets close to the black hole and then can't escape, right? Space-time bends it back in. But you're also gonna have some emission, some light that's traveling by that just misses the black hole, just misses that point of no return, which we call the event horizon, which is also a fantastic Lawrence Fishburne movie from like the 80s. So you have this emission that just misses, and so it gets bent around that black hole, and you see it on the top and bottom. It appears to us as if it's on the top and bottom. So here is, on the top, this is an actual model prediction, an astronomical model prediction of what this accretion disk will look like. You can see it's faint on one side, and that's because as this material swirls around, some of it's coming towards you at some points, and some of it's coming away from you. And so that difference in motion creates a slight difference in the brightness on either side. And so here is, if anybody saw the movie Interstellar, this is the massive, supermassive black hole Gargantua from that movie. And they didn't get it quite right with the brightness on different sides. But rumor has it that they did have it right, but then they changed it because they thought the audience would be too confused if it was bright on one side and faint on the other. So they went for pretty picture over accuracy. And so then, of course, just a couple years ago, we were able to take the first direct image of a black hole using telescopes spread out all over the globe, acting together as one. And so this is a nearby supermassive black hole, M87, that's 6.5 billion times the mass of our sun. So you can see this difference in the brightness. All right, so there's a couple other detection methods that I'm going to skip over. And I want to end with the question of, will a black hole swallow the Earth? That would be a very 2020 thing to happen right now. So will a black hole swallow the Earth? To understand the answer to that question, we have to understand how far away black holes are to understand, their potential danger. So here's an artist's rendition of the Milky Way, our galaxy. And so I pointed out the sun here. So our sun is one of 200 billion stars in our galaxy. So let's say that our solar system is this cookie. Hold it up, got it? All right, so let's say the sun is a speck of sugar in the center of this cookie. On that scale, the Earth would be about 1 millimeter away, less than 1 millimeter away. And Pluto would orbit around the edge of the cookie. So how far away do you think the next cookie would be, the next stellar system cookie, the next closest star after our sun? It would be about 2 soccer fields away. So I'm in LA, so that means I'm a Dodgers fan. So it would mean from sitting in your seat in the stadium to your car out in the parking lot. And I'm not talking about the good parking, I'm talking about the bad parking. That's about how far away the next star would be if our sun was compressed down to a speck of sugar. So in this, and so then, here, let's see, I have a diagram So here are some of the closest black holes that we know of in our galaxy. And our closest black hole, this V616 Monoceros, is on this scale where the sun is a speck of sugar and our solar system is a chocolate chip cookie. The nearest black hole would be about 130 miles away. So that's like the distance between me here in LA to many of you in San Diego. So the point is that the universe is very vast and very empty. And our galaxy, the Milky Way, has 200 billion stars in it. So our sun is just one of 200 billion stars. And there are only 1 million black holes in our Milky Way. So that's half of 1% of all of these stars are black holes. So black holes are far away and they're few and far between. And so we're not really at risk of being swallowed by a black hole.
You.
Thank you. You can eat the cookie now if you want.
Okay.
So we are sitting here on our speck of sugar and our cosmic cookie, which is just one of 200 billion stars in our galaxy, which, by the way, is just one of hundreds of billions of galaxies out there in the universe. And so all of our cumulative joys and woes are a mere blip in these vast cosmos. But it's something that we all share. So let's take care of each other. And if we can figure out that you can take a massive astronomical object and squeeze it down into a zero volume, and then we can figure out how to detect these things, even though light does not escape, I'm confident that we can find a way out of our current predicament. Thank you. I'm done.